Okay. This is the discrete math lesson on the divine proportion slash golden ratio. There has been in the history of mankind a pull or a desire towards a certain ratio that can be expressed visually and numerically. Um, it's just something that has been engraved on our DNA, on our souls. And it is this concept of the divine proportion, the golden ratio. Those are the names given to it. And given the fact that they refer to it as being divine or golden, just hopefully shows how impactful this particular number has been on people's lives. So let me give you a brief definition as to what the golden ratio is, and then let me go into some of the details as to why people consider it to be so important. So first and foremost, I have this line drawn on my paper, and that's going to come into play for the definition that I'm going to give you. The golden ratio is a line divided into two sections in such a way that the ratio of the whole to the larger part the ratio, I'm going to put these in quotes, the ratio of the whole to the larger part. That's the first portion right there, is the same as the, quote, ratio of the larger to the smaller, end quote. You refer to it as maths. I'm assuming that you're not from this country, but that's awesome. I love calling it maths. But back to this. A line divided into two sections in such a way that the ratio of the whole to the larger is the same as the ratio of the larger to the smaller. Now, to give a bit of perspective on that, I've seen people refer to it as, well, assume that the larger ratio, the length is A, or ratio, I'm sorry, the larger length is A, and the smaller length is B. By this definition, the ratio, the fraction of the whole, which the whole thing would be A plus B, to the larger part, which is clearly the A in this case, is the same as the ratio of the larger to the smaller. This is the general concept of the divine proportion. Now, I mentioned a number earlier, a number that would be expressing this particular ratio. Now, in order to actually exemplify this number, you would have to let the value of B just equal to a unit. So actually, I'll do that on this next page right here that you can see. There we go. If I were to let the value of B on that line just be a unit or a value of one something, whatever it is that you want it to be, you get the following fraction, in which you can solve for A. If you were to solve this for A, you would end up with A squared equals A plus 1. You can get a quadratic, A squared minus A minus 1 equal to 0. It cannot be factored, so you would have to go about using the quadratic formula. Negative B plus or minus the square root of B squared minus 4 times A times C all over 2 times a. Now, what this actually becomes when it's all simplified, said and done, is the fraction. Now, can't really do the minus portion, because if you did the minus portion, you would get a negative answer, which, since we're dealing with the lengths of a line, can't really do anything. So I'm just going to do the plus. It's going to be 1 plus the square root of 5 over 2. Just for the sake of argument, if I were to actually do that in my calculator right here, parentheses 1 plus the square root of 5, close it up, divided by 2, gives you the approximate number 1.618034 if I had to go a little bit farther. Now, this number is quite possibly the most important number in the history of mankind. More important than pi, more important than any whole number that you can think of. This number, this ratio, which the ratio that they're referring to, I can move some of these things around a little bit. The ratio that they're referring to, golden ratio, is 1.618 to 1. That's the ratio that they're referring to. And of course, this is an approximate number. This number, quite possibly, again, is the most important number / ratio in the history of the world. And I want to explain to you why that is. Now, for the sake of argument, this number, approximately 1.618, is referred to by its own Greek letter, similar to pi, except it's phi, P-H-I. It's so important, similar to pi. Pi was given its own designation, its own symbol, so is phi. But again, like I said, phi is much, much more important. Now, to go into some of the details as to phi, I have a book page that I want to show you. Let's bring that into frame right here. I'll zoom in just a little bit so you can see what I'm referring to. But basically, this guy named Gustav Fenchner, he was a psychologist, and he was very interested in the ratios of phi, and did this experiment where he showed a large number of people, I don't know how many people he showed, but these different squares. And then he asked these people to pick the rectangle that they found to be, in his words, the most pleasing. And then he took all of their results and he graphed them. Now, obviously, one person's opinion is just an opinion. It's just what they think. It's just how they feel. But a plurality of people, approximately 35% of people, he found, and you can see it peaking around that, picked the ratio of rectangles that was 5 to 8. Now, if you do a little calculation right here, and I'll show a few of them. I'll show the ones surrounding 5 to 8. 23 divided by 13, 8 divided by 5, 3 divided by 2. If you look at these three that are the most selected, the one that is closest to the value of phi, the one that, the number that I deemed the most important in human history, was 8 over 5. That was the one that had the ratio most similar to phi. It's something that, again, human beings may not be able to verbalize. They may not be able to conceptualize. They may not be able to say, oh, yes, this is why we pick what we pick. It's just something that we prefer. Now, if you think about the televisions, the ratio of televisions, most televisions today, the vast majority of televisions today, are in a certain ratio aspect, in which they're either 16 by 9 or 16 by 10. It's what we consider to be widescreen. If you look at 16 by 10 or 16 by 9, you can see that these numbers, these ratios, surround phi. They surround the golden ratio, 1.618. It's pleasing to the eye. It's visually appealing. It's something that we may not be able to verbalize why it is what it is. It just works. It's something that our brains just prefer. Let me give you another visual as to phi. I'll get another piece of paper here and zoom back out. Oh, come on, you. Okay. Hopefully that worked. I don't think it did. That's not bad. Okay. So for example, I'm going to try and draw this to the best of my ability. Actually, no, I'm going to have to do that sequence first. Yes, I'm going to have to do the Fibonacci sequence first before I show you another visual example. There's a mathematician who went by the name Fibonacci, and he was obsessed with a series of numbers that went along the lines of this: 1, 1, 2, 3, 5, 8, 13, 21, 34, etc. And the way that the sequence typically began, he let the first term of the sequence equal 1. He let the second term of the sequence equal 1. And then from there on out, he let the next term always be the addition of the previous two terms. And this is how it was typically expressed. So, for example, you start with a 1 and a 1, and then, well, 1 plus 1 is 2. And then 2 plus 1 is 3. And then 3 plus 2 is 5. And then 5 plus 3 is 8, etc. See that? Now, this Fibonacci sequence has a very unique property where as you go farther and farther and farther down into the sequence, a unique thing begins to happen. If you were to, let's say, make a little bit of a table here, Fibonacci number, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll just go down 9. And then the Fibonacci number would be 1, 1, 2, 3, 5, 8, 13, 21, 34. If you were to take the ratio of, let's say, some Fibonacci number k divided by its previous number, can't do the first one, but 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 2 is 1.5, 5 divided by 3, why can't I do this off the top of my head? That's what, 1.67, I believe, rounded. I'm going to go to the calculator for the rest just to make it a little easier for myself. Yeah, 1.67, it rounds. 8 divided by 5 is 1.6, as we saw earlier. 13 divided by 8 is 1.625. 21 divided by 13 is 1.6154. 34 divided by 21 is 1.6190. If you continued this farther and farther and farther and farther down that rabbit hole, eventually the ratios would get closer and closer and closer to phi. The general idea being, I'll write it over here, an f divided by k over, or I'm sorry, f of k, whatever term you are in the sequence, divided by f of k minus 1, is approximately phi as the value of k grows larger. The farther down the sequence that you go, the closer and closer to this unique value of phi that you get. And again, that value of phi being parentheses 1 plus square root of 5 divided by 2. It's a very unique number. Now, again, that visual thing that I was referring to, I needed to talk about the Fibonacci sequence first before I went into that appealing visual aspect. Now, if you notice the Fibonacci sequence, 5 and 8. Again, those rectangles that you go back to, 5 and 8, or the ratio of 5 to 8 being visually appealing. Again, the ratio of 5. It's just one of those crazy things. If I talk about that Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, 21, if I were to talk about that, I could draw something quite unique. Here, see if I can draw this. Start with the square of 1 and another square of 1. Well, there's your 1 and there's your 1. There's a 2 by 2. I'm sorry, it's not 2 by 2, but it's a 2 squares there. Here's 3. Oh, I know, I messed that up. I'll try that one again. I messed that up. I always mess up the 2 part, and when I mess up the 2 part, it ends up screwing me up for the rest of the way. So let me do that again. Fibonacci sequence. There's a 1 by 1 square. There we go. There's a 1 by 1 square. There's a 2 by 2 square. Now we're cooking. Here's a 3 by 3 square. Oh, I went the wrong way, didn't I? Yeah, I totally went the wrong way. I'll go this way. Here's a 5 by 5 square, and I'll do one more. This is all mess up here. I'll fix that later. And then I want 8. And here's an 8 by 8 square. I can't fit in the next one, the 13. I knew that I wouldn't be able to. But the general idea behind using these squares that match the Fibonacci sequence, if you were to continue it, create what is known as a Fibonacci spiral. Again, that's a terrible way of doing it. There's much more visually appealing ways to look at that Fibonacci spiral. And I did do a printout that does exemplify it a little bit better. Here's what we got. This Fibonacci spiral, each little part of the spiral expands out at the ratio of phi, as you can see based on those numbers. It's created in the same way that I just created my terrible picture, which each little square represents a 1 by 1, a 2 by 2, a 3. I'm sorry, a 1 by 1, a 1 by 1, a 2 by 2, a 3 by 3, a 5 by 5, etc., and expand out in this spiral fashion. This concept of the spiral based on the Fibonacci numbers have been known for centuries, and clearly in one of the most visually appealing paintings of all time, Da Vinci created it based on the spiral. He was well aware, Da Vinci was well aware of the concept of phi and how it could apply to something to be much more visually appealing. And I'll go into greater detail of that later. Now, this Fibonacci sequence is hidden in so many aspects of our lives. And I'm going to get into the humanistic aspects and the naturalistic aspects of that in a little bit. But let's talk a little bit about Pascal's triangle. Pascal's triangle, Pascal, the mathematician Pascal and the mathematician Fibonacci never met each other. Pascal devised this triangle made up of numbers, in which he found a lot of different applications of this particular triangle, which the applications of this triangle would have to be a lesson for another day. From probability to algebraic binomial expansion. It's insane how this thing just bleeds into different levels of mathematics and life and whatnot. The way that this triangle is devised is quite simple. Obviously, there are ones going down the side. every row in the triangle has one more number than the previous row. So the first one starts with 1, and then 2, and then 3, and then 4, etc. When we get to this number right here, this number is the addition of the two numbers on a diagonal just above it. And that's how the triangle bleeds down. 1 and 2 add to get 3. 3 and 3 add to get 6. 4 and 6 add to get 10. 5 and 10 add to get 15, etc. This thing could be expanded pretty much forever. Yeah, 35, 21, 7, 1. And again, if you're familiar with combinations, probability, binomial expansion, as I mentioned earlier, that's how this thing kind of comes into play. But one amazing aspect, again, Pascal never meeting Fibonacci, on this diagonal, I get a 1. On this parallel diagonal, I get a 1. On this diagonal, I get a 2. Parallel diagonal. And on the diagonal, I'm adding up the numbers on the diagonal. I get 3. On this diagonal, I add them all up. I get 5. On this diagonal, 1, 4, and 3, I get 8. 1, 5, 6, and 1 equal 13, etc. Now, of course, I'd probably have to continue the Pascal's triangle in order to get it, but basically, the Fibonacci sequence can be devised from Pascal's triangle. It's absolutely insane how that actually just randomly shows up. It's quite insane. One major thing that anybody who draws or paints or does photography, one major thing that they'll talk about is the rule of thirds, in which they try to explain how when you're taking a picture, it's good to divide up. And there are a lot of cameras that have this crosshairs already on them, but the rule of thirds, where they divide up things into thirds. And anybody who does photography or painting, they'll say that, oh, things are a bit more visually appealing if you are dividing up your screen like this and then putting your subjects like on one of the crosshairs. It's some weird visual thing where like, oh, you take better pictures that way, blah, 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 blah. Well, what photographers and painters have found rediscovered today, especially photographers, is the rule of phi. Instead of the rule of thirds, creating a thirds grid, they actually create these grids based on the rule of phi. And it's quite remarkable how these things come into play. I think it's something like this, I vaguely remember. But it's slightly off from the thirds. And it's closer to something that, well, again, visually, it's like, oh, wow. People, when they take pictures and they put certain things within this spiral, it ends up being much more visually appealing. And I have another picture to kind of show that. Right here. And again, within the human body, these Fibonacci spirals are based on that phi grid. That Fibonacci spiral is based on the Fibonacci numbers, which increase at a ratio of phi. And you end up with something quite remarkable. And you can see this picture just shows so many things all at once. It shows the ratio of the spirals in the human ear, in the human face. In fact, and they've done studies on this, human beings whose bodies are much more proportional, naturally proportional to the value of phi, are much more considered to be attractive. It's scientific in that sense. I mean, obviously this can't necessarily be proven because beauty is in the eye of the beholder. It's more of a subjective statement. But they found that people that are more attractive fit this natural ratio of phi. It's insane. In fact, if I go a little bit deeper into it, going back to Da Vinci and what he knew, now I haven't been able to print something out. I don't really want to show this only because there's, if you look up the real one, there's a bit of nudity in it. But if you Google Vitruvian Man and have some sort of golden ratio, divine proportion, or something like that, you're going to see some images that show how Da Vinci was able to look at the human body and actually devise all of these ratios that end up showing phi. It's quite remarkable. Now I'm going to draw my own Vitruvian Man here, which is terrible. There's my Vitruvian Man. Imagine that the elbow was like right there or some junk like that. Yeah. If you go from the shoulder to the fingertips, if you go from the shoulder to the fingertips, and then from your elbow to your fingertips, and divide them. So length of arm divided by length of elbow down, it's approximately phi. If you took an average of all human beings, and I did this actually in a class I had last year with 20 some odd students. I had every student measure the length of their arm from their shoulder to their fingertip and their elbow to their fingertip. And everybody gave me their numbers. I put everything into a list. And I figured out the ratio of everybody, and everybody's ratio was completely different from each other. Some had ratios of 1.3, 1.9, 1.7, 1.6. All these ratios were just slightly off. Well, of these 20 some odd students, I did the average, and the average was almost spot on, approximately 1.618. It was insane, and everyone started freaking out. There were a bunch of high fives. I was probably just high-fiving myself, but it's embedded within us. There's a video that I shared with the class the other day in Google Classroom, and I'll have to put that link in the description when this video is done. But this video showed how even on the DNA level, on the molecular level, the spiral of our DNA spirals at a ratio of phi. It's not only in our DNA, it's built into the human body. It's something that's encoded into our brains to be visually appealing. It is absolutely insane. Let me talk about the Pentagon, or the pentagram, I should say. Now, this isn't going to be drawn perfectly. But I'm going to draw it to the best of my ability. Imagine a pentagram, something along the lines of this. I'll try and draw this as best I can, because again, I'm drawing this freehand. That was okay. But if you had a regular pentagon, or pentagram, let's say, a regular meaning all the angles are the same. Like, again, I can already see this is off, but just imagine a regular one where all of the images are perfect or whatever. And I'll do this in red and green right here. But if you had a regular one, and then you took the ratio of that line to the ratio of this line, that ratio would be phi. If you had one regular, and I'll kind of put this down here, length of red divided by length of green is approximately phi, which is approximately 1.618. I can show you a different ratio within that pentagram. And again, I'll try to draw this as best I can. That was a terrible noise. That one's even worse, but whatever. Haven't figured this out. If you took the length, this longer length on the pentagram, and divided it by the length of the outside, again, that ratio would get you phi. Hopefully you can see that a little bit better. There we go. I can, it's all over the place on this thing. Now, as I'm drawing the next one, there's this concept known as Platonic Solids. If you Google it, it's absolutely phenomenal. These Platonic solids, and I'll show you one. I actually have one of them in a puzzle form that I'm going to show you in a moment. But these Platonic solids, a lot of them are just made up of basic shapes. They're three-dimensional shapes. But a lot of them have this ratio of phi. I'll show you how it applies to some architecture in a little bit as well. But again, all of these different things, you can see if I took the length of the red and divided by the length of the green, if it were drawn correctly, it would give you that value of phi. Here's one of the Platonic solids that I was referring to. See that right there. This is a puzzle known as a megaminx, but it is in the shape of what we call a dodecahedron. And you can see every single side is made up of a pentagon, a regular pentagon. There are 12 sides to this thing. Dodecahedron is what they call it. But again, if I was comparing, let's say, this pentagon to this, oh, there we go, to this. Oh, I had it right the first time. Duh. Oh, this thing is drawn weird, yeah. But anyway, regardless, if there was this length right here, and actually assume that these two were connected right here, that would be what that one was referring to. Probably a better one is this. This length for the first one, this length, this length. If you were to divide them again, it would be the value approximately to phi. And again, it's visually appealing. Why does something like this look so complete and nice to us? Don't worry about the colors, worry about the shape. It just looks complete. Mentally, psychologically, it's encoded into our DNA. Let me show you some of these things that I have in the book right here. See if I can find, I have these pages marked. Here we go. Here's one right here. And I'll zoom in on this one so you can see a little bit better. There we go. This is the design for the Great Pyramid of Giza. And they may not have known the numerical value of phi, but what they were able to do was they created this shape based on the ratio. They were able to measure it out and base it on the ratio. It's quite insane the way that they did that in Egypt. If you look at the Acropolis in Greece, the way that they know that the Acropolis in Greece was designed was it was designed with this idea of phi in mind. It is quite insane how they were able to figure these things out. Now, oh, I didn't show you this one earlier. I got to show you this one. Here we go. Look at this picture. I got to get the glare off of there. There we go. There's the glare off of that. Look at that picture. You can see it in the little description. This is a zoomed in picture of the cochlea, of the human inner ear. Look at that spiral. That spiral is in the ratio of phi. Look at this right here. That is an empty human hair follicle in your skin. When it's pulled out, it ends up being a spiral of phi, or a Fibonacci spiral. This thing is absolutely insane how much it comes into play. Even in nature. Look at this. The way that leaves are grown on a stem, they're grown in such a way where each leaf can get the maximum amount of sunlight. It's crazy. The maximum amount of sunlight, but the way that they grow in a spiral. And the spiral is in the ratio of phi. This number is so important. It's just that human beings have not been able to visually or verbally be able to explain why it is what it is. Quite insane. Oh, hey, Kyle. Yes, you happen to be late. That's okay. You can go back and watch the whole video. But actually, you're here for the final demonstration. Kyle, what I've been talking about for the past little bit has been this number phi. And this number phi is approximately 1.618, which is equal to, or approximately equal to, 1 plus the square root of 5 over 2. It is the most important number in the history of mankind. I've shown it in an algebraic way. I've shown it in a numerical way. I've shown it in countless naturalistic ways, architectural ways, psychological ways. One way I showed it was using this pentagram, or this Pentagon inscribed shape. It's quite beautiful the way that this thing shows up. One thing I wanted to show, and I was saving this for last, is this apple. Now, we're all very familiar with apples to an extent. I'm pretty sure people just bite it around the sides like that, which is perfectly fine. But there's something hidden inside of this apple. Now, I don't know if this will work the way that I hope it will, but I'm still going to do this demonstration nonetheless. I have a knife. I'm going to try and cut this apple properly, directly through the core. I don't want to break it. Look at that. Look at that. This five-sided shape hidden inside of your apple. It grows with the ratio of phi in mind. Phi, PHI, the ratio that is approximately 1.618. It is hidden within numerical patterns. It is hidden within the human body, at the DNA level, at the bone structural level. It is encoded into our DNA. It is visually appealing to the mind. It is, again, the most important number on the history of the planet. It's not just apples that do this thing. It's not just apples that do this thing. I'll come back to the apple in a minute. I'm going to eat that thing later. It's going to be great. Where is this thing? I had a page bookmarked and I lost that page because I was so focused on other things. No, here we go. Check this out. I found a page with the spiral. You can see that spiral that we talked about earlier, and the Nautilus shell having that exact same spiral. It's quite remarkable the way that this thing works. Oh, here we go. Right there. In the spiraled patterns of a pineapple. In the spiraled patterns of the seeds of a strawberry. These things show up like crazy. It's absolutely insane. The most famous example, if you actually look at it in nature, is the spirals within the seeds of a sunflower. It's, again, this thing is encoded in every aspect of life, from human beings to animals to plants, on the molecular level, in our visual appealing level. It's quite insane. Now, I am, for my discrete math class, for the lesson, I am going to be assigning them something soon, not today, but I am going to be assigning them something today in regards to phi and the divine proportion and some things that I'm going to be looking for. That's just so cool looking. Look at that. Anyway, but if you have any questions, of course, you can email me. But this officially, technically, is the end of the lesson. So, yay. I'm going to stop it there. I may be on live later today. I have not decided yet. But stay tuned. Make sure that you are subscribed. Make sure you are ringing that notification bell just in case. And Kyle, if you're here sooner, maybe we can have a conversation. But, oh, there is Joe. You just got here? I'm sorry about that, Joe. I've been on for almost 50 minutes. Well, I don't have to. I mean, I can stay on for a few more minutes. I'll just put in the timestamps when I eventually do this thing that this was the official end of the video. I can hang out for a couple minutes. Thanks. Here, tell you what. Here's what we'll do. YouTube decided it wanted to notify me late. Okay, here's what we'll do. I will end this video. I am going to go get something, and I will be back on live. I'll be back on live in, like, let's call it 5 minutes or so. Okay? So I'm going to end it now. But if you're interested, maybe I'll take like a half an hour and we'll just we'll hang out and we'll play a video game or something like that. But I'll be back in like 5 or so minutes. Hang tight.